Swayam Prabha. Digital India. Educated India.
Hello everybody, welcome to today's lecture on recycle. So usually in most of the industries, the streams which leave a reactor or a particular process is not been fully converted into the desired products or has not been fully purified, and the process might still have to be done multiple times. So in such a scenario, setting up multiple processes or equipments for the same process would not be cost effective. So what people do is, the streams which are leaving the process will be sent back into the process for further processing. So this type of a setup is called recycle. We will talk about recycle and how it is useful for chemical and biochemical industries, and we will solve some example problems to try and understand the fundamentals of recycle when it comes to material balance calculations. So what happens is, reactions, if you consider reactors, reactions never go to completion. In most cases you would always have incomplete or partial reactions. That is why we learnt all the terminologies associated with them and we were performing calculations related to them. So in this case what happens, the unconsumed reactant which leaves the reactor is a wasted resource. If you just discard it, you are actually throwing away money because you have spent a lot of money to procure these reactants. So you would not want to waste them. So instead what you do is, you can try to separate these unconsumed reactants using some downstream operation and send this back to the feed. So now your feed not only includes the fresh feed which has been purchased, but also includes the recycle which has been taken from the process and sent back into the system. So this particular process is called as recycle, and it helps in reducing costs associated with a process. A term recycle ratio is used to define how much of the component is being recycled. So it is defined as the ratio of mass of recycle to the mass of fresh feed. So this can be done for non-reacting systems also. For example, distillation is one system where you can consider having recycle. We will look at different examples for such a scenario. So look at this process. The first process shows two different feeds entering into a process and leaving as products. So you have another system where you have two processes connected to each other. The first one has two inputs and one output, and the output for the process 1 goes into the second process and products are formed. So what you can do here is, the output of the products process 2 can actually have a separation system where products are removed and the unreacted reactants or the raw material which needs further processing can then be recycled back into the feed for the process 1. So this is a flow chart representing how recycle systems work. So when we talk about processes with recycle, we need to understand that they are always multi-unit processes. This is because the overall system which we consider would have the process of interest, and it would also have a splitter or a separator which helps in taking some of the product stream leaving the process and sending it back to the feed, and then it would also have a mixing point where the recycle is mixed with the fresh feed which is sent to the process. So thereby you get at least 3 separate single unit systems combining together to form the recycle system. So we need to understand that the feed which comes in before the recycle, the feed which is sent before recycle is called as a fresh feed, and this fresh feed when mixed with the recycle forms the total feed or the gross feed which enters into a process and then goes through the process and products are removed. Here one term which we need to understand is, material circulates without accumulation. What do I mean by this? Accumulation will be 0 for any system which is chosen. Let us consider a simple system for recycle. So you have an input and an output for a process, and a splitter is used to separate out some of the product which is leaving the system and is sent back into recycle. Now, if we were to consider mass flow rates during the initial, during steady state, what will happen is you will have 100 kilograms per hour entering and 100 kilograms per hour leaving the system. But the recycle stream could be anything, could, if the recycle ratio is 5, you would have this as 500 kilograms per hour of recycle being sent back in. So, now what you do is, if you consider this overall system, so the streams which are crossing the boundary are input which is 100 kilograms per hour and output which is again 100 kilograms per hour. So, this means there is no accumulation inside. If you were to consider a different system, so let us say you consider the system, so this is for the overall system. So, if we were to consider the mixing point, so the mixing point would then have two inputs, which is input being 100 kilograms which is the fresh feed plus 500 kilograms which is the recycle feed entering into the system, and output would be this gross feed which is basically the summation of these two, which is again 600 kilograms per hour. So, thereby this is also input equals output. So, similarly, if we were to consider this particular system which is the splitter, what you would observe is the splitter would also have an input which is equal to the mass of the gross feed. So, which would be 600 kilograms per hour, which is the gross product which is coming out, and your output would be the summation of your final product and your recycle stream, thereby being 100 plus 500 giving you 600 kilograms per hour. Again input is equal to output. So, I have considered a simple process where there is no reaction. So, I have not ignored the generation and consumption terms, but what you can see here is everywhere input is equal to output. Because of this, we understand that accumulation is 0. So, this is despite the fact that there is 500 kilograms per hour of recycle stream which is circulating within the system. However, this is not considered accumulation because it does not build up over time, it does not change with respect to time. How is this steady state achieved while keeping material in circulation without accumulation inside the system? So, let us consider the initial transient phase where you have the unsteady state of the process. So, what you have here is in the initial phase you have this particular process where you have 100 kilograms per hour entering and 100 kilograms per hour leaving the system. So, without recycle the system is in steady state. Now, if I were to take 50 kilograms out of the product and send it back here, so what I have here is 50 kilograms per hour as recycle. So, this will now become 50 kilograms per hour. So, now the process is at unsteady state. What happens immediately after this over a period of time is this 50 adds up to this 100 and your gross feed becomes, gross now becomes 150 kilograms per hour. So, which means your gross product should also be 150 kilograms per hour, thereby if you were to continue taking only 50 kilograms in recycle, this product stream which you recover would be 100 kilograms per hour. This happens over a period of time. So, this initial period where you have unsteady state would be the transient phase of the process. So, finally, you reach steady state like this, and you can continue doing this to make sure that this particular value for recycle is built up to achieve the required recycle ratio. In the example we saw in the previous slide, we had assumed a recycle ratio of 5, thereby this was being 500. So, if you consider that, what we would be doing is instead of leaving this as 100 kilograms leaving, we can still take out 50 of this and send it back, which means the recycle stream will now become 100 and your gross would become 200, thereby your gross product would also become 200, making sure that your final product would again be built up if you were to continue having only 100 kilograms per hour recovered as recycle. So, by doing this repeatedly, we can actually build this recycle stream to the particular desired mass we want, so that we have the desired recycle ratio, and this is done without affecting steady state. Accumulation does not happen for any of these processes. As I already explained, if you consider any system within this process, you would find that there is no accumulation. Assuming no reaction, you would always have input equals output. If you understand this particular concept, it brings in a lot of clarity when it comes to recycle systems. With that, let us move on to how we would solve a recycle problem. As I already mentioned, any recycle system is a multi-unit process. Just like any other multi-unit process, identifying the right system to study is a very crucial aspect for performing calculations. So, if you consider this example where you have a mixer and a splitter and the process with a recycle stream, you end up having multiple systems which you can consider. You can consider the overall system, which basically engulfs the mixer's process and the separator, or you could consider the mixer as a system, or the process as a system, or the separator as a system, or combinations thereof. So, identifying which system you want to start with will help in solving the problem. So, this would be similar to solving any other multi-unit process. Let us consider recycle systems without reactions. Some processes where you have such recycle without reactions would be distillation, crystallization, heating and refrigeration, and so on. So, in distillation, we already saw that separation is not complete. You always have some separation and you would have a mixture leaving both in the bottoms and in your distillate. So, it is important to recycle to ensure that you get the highest level of purity. Crystallization again is a process where you might want to send it back in, so that the saturated solution can be further cooled to get more crystals out. Heating and refrigeration are systems where you perform recycle to ensure that the energy which is present in these materials which are leaving is utilized to ensure that the process uses the energy rather than wastes it by throwing it out of the system. So, let us take distillation as an example. So, here is a process which describes distillation. What you see here is a feed which is entering into the system, which is the distillation system, the feed entering into the distillation. So, you would usually have two particular products leaving. So, you have one which is the bottoms product and the other which is the distillate product or the overhead product leaving the system. So, the overhead product which is leaving the system leaves with the volatile components. So, this has all the volatile components, and this is basically cooled down to make sure that some of the volatile components are condensed to form the liquid, and this liquid is sent back in the name of a reflex. Similarly, the bottoms product which contains the non-volatile components or the less volatile components, so to be more accurate it would be less volatile components, this leaves as the bottoms product, and this can actually be recirculated back into the distillation column through something called a reboiler. So, this reboiler makes sure that the liquid stream present in the bottom gets evaporated, so that the vapors are sent back in. By doing this repeatedly, you ensure that there is a high percentage of separation and you get a highly pure product. So, by doing this you would get a highly pure product which is the overhead product, and your bottoms product would also have more of the less volatile components and making sure that your separation is quite efficient. Let us see a couple of example problems which will help us in understanding this and understanding how to perform material balance calculations for such a system. Seawater is to be desalinized using reverse osmosis. The scheme is shown here in the figure. You are asked to use the data given in the figure to determine the rate of brine which is being removed and rate of desalinized water which is being produced, and the fraction of brine leaving the reverse osmosis cell that is recycled. So, we need to calculate how much brine is being removed, which is B, and how much desalinized water is being produced, which is D, and we also need to find the fraction of brine which is leaving the reverse osmosis cell that is being recycled. So, we need to know what the recycle stream would be. So, let us see how we can go about calculating these values. Just like any other material balance, the first step for solving this material balance problem would be identifying the basis. So, in the problem statement it has been given that 1000 pounds per hour of seawater containing 3.1% salt is entering, which means our basis will be 1000 pounds per hour of seawater fed. This would be the basis we start with. So, now the next step is to identify the right system to study. We have the information about the concentration of salt in the fresh feed. We also know the concentration of salt in the brine waste and the concentration of salt in the desalinized water. So, this means using this particular system as the overall system would be a good way to start. So, now assuming the overall system as the system of interest, let us start writing the balance equations. We can write a total balance equation which would be 1000 pounds per hour of feed which is coming in will be equal to B, which is the brine waste leaving, plus D, which is desalinized water leaving the system. So, the next balance we can write would be the salt balance. So, if we were to write the salt balance, it would be 0.031 times 1000 equals 0.0525 times B plus the concentration of salt in the desalinized water is given as 500 ppm, which means it would be 500 times 10 power minus 6 times D. So, now we have two equations and two unknowns. Solving them we can get B and D. So, B would be equal to 586 pounds per hour and D would be equal to 414 pounds per hour. So, with this we have calculated the amount, the mass of desalinized water and the mass of brine waste which are leaving the system. Next step is to calculate the fraction of the brine leaving the reverse osmosis cell that is being recycled. For this we need to get the information about the recycle stream. We need to know the mass of the recycle stream. So, how do we calculate that? What system can we use? There are two systems which can be chosen where the recycle stream will cross the boundary. Those would be the mixing point and your splitter. Considering that we can write only one balance equation for the splitting point, it would be wise to start with the mixing point because we would have two unknowns to solve for in this particular equation. So, let us look at the mixing point as the system of interest. For the mixing point we can write the total mass balance as 1000 plus R, which is the input, would be equal to the gross water salt water which is entering into the reverse osmosis cell. Let us call that G, and you would have a salt balance that we can write. The salt balance would basically be 0.031 times 1000 plus 0.0525 times R would be equal to 0.04 times G. So, you have two equations and two unknowns. So, using this you can solve for R, which is the recycle stream. R would be 720 pounds per hour. So, in this equation I hope you understand why I chose to write 0.0525 times R. This is because of the fact that you have a splitter here. So, if you remember from the earlier lectures, for a splitter the concentration of dissolved components does not change because only the stream is being split into multiple streams, which means the concentration of dissolved components will be the same, or the composition will be the same in all the streams which are entering and leaving the splitter. This means the concentration of brine waste, which is 5.25% salt, would be the same in the brine recycle also. So, the brine recycle would also contain 5.25% salt. Considering that, I have written 0.0525 times R as the amount of salt which is entering through the recycle stream. So, now that we have R, we can calculate the fraction recycled as 720 divided by 720 plus 586, where 586 is the amount of brine which is leaving the system So, the total basically is 720 plus 586 giving us a fraction of 0.551. So, more than 55% of the brine waste which is actually being produced from the reverse osmosis cell is being recycled. So, only less than 45% is being thrown out as brine waste. So, hopefully you were able to follow this problem and you were able to understand the logic behind choosing the systems and understanding the compositions which have to be used for the salt concentrations. With that, let us move on to the next example problem. The protein purification system of continuous affinity recycle extraction combines the advantages of well accepted separation methods like affinity chromatography, liquid extraction and membrane filtration, while avoiding the drawbacks inherent in batch and column operations. The technical feasibility of the CARE system was studied using beta galactosidase, which is using an affinity purification as the test system based on this process given below. What is the recycle flow rate in terms of milliliters per hour in each of the stream? Assume that the concentrations of U are equivalent to the concentrations of beta galactosidase in the solution and that steady state exists. So, what has been given to us is this particular stream contains a feed into the absorbing stage and a waste, and you also have a desorbing stage which has a desorbing buffer and a product which is leaving the system. You also have recycle between the absorbing stage and the desorbing stage which are happening both ways. The composition of these streams are also given. You have been asked to calculate the recycle flow rate in terms of milliliters per hour. So, if you remember earlier I had mentioned that balances have to be written only for moles or masses. We cannot write balances for volumes unless we make one crucial assumption. The assumption is the density does not change. So, as long as the density does not change, we can assume that the volume is also conserved. So, making that assumption for this problem, we would be able to solve for the volumetric flow rate of the recycle stream. So, let us start with identifying the bases. So, you have different flow rates which are given. So, your bases can basically be written as various flow rates given, which would be the given flow rates as your bases. Now, as I mentioned earlier, the assumption we make is density is a constant. So, the next thing we have been given is steady state is maintained. So, for steady state to be maintained for these two processes, we need to ensure that the flow rate of the feed and the waste are equal for the absorbing stage and the flow rate of the desorbing buffer and product are equal for the desorbing stage. This can happen only when the volumetric flow rate of the recycle is the same for both these streams. So, the recycle flow rate, volumetric flow rate would be equal for both these streams. With that, we now have to choose a system to identify what this flow rate for the recycle would be. As we want the recycle stream to cross the system boundary, we could either choose the absorbing stage or the desorbing stage for as the system for performing the calculations. In this case, I have chosen absorber as the system of interest for performing calculations. We could either write a total balance or a component balance. So, the total balance would not be very useful here. So, hence we would use the component balance. The total balance would be trivial. So, component balance will be useful for calculating the volumetric flow rate of the recycle stream. So, we will use the component balance which is the beta galactosidase, which is U. So, the component balance here would be beta galactosidase enters as 600 times 1.37 plus recycle times 5.2, and this leaves as 600 times 0.08 plus recycle times 19.3. So, using this balance equation, we can calculate R, which is the volumetric flow rate, as 55 ml per hour. So, this is a simple problem where we were able to perform material balance calculations to calculate the volumetric flow rate of recycle entering and leaving the system, which is the absorbing stage. So, with that we can come to the conclusion for recycle problems without reactions. So, in the next lecture we will talk about recycle problems with reactions, and we will also perform some tutorial problems related to recycle without reactions. Thank you.